Welcome to the listening section of the TOEFL mock test, brought to you by Spinta. This section measures your ability to understand conversations and lectures in English. In this section, you will listen to several conversations and academic lectures. Each conversation and lecture is followed by a number of questions. You will hear each conversation or lecture only one time. You may take notes while you listen. You may use your notes to help you answer the questions. Some of the questions will replay part of the audio for you. Answer the questions based on what is stated or implied by the speakers. You must answer each question before moving on. You cannot return to previous questions in this section.
Good morning, everyone. Today I want to talk about coral reef resilience in the face of climate stressors. Reefs are often described as the rainforests of the sea because of their biodiversity. They provide habitat for thousands of species, protect shorelines, and support fisheries and tourism. Yet they are under threat from warming oceans, ocean acidification, pollution, and overfishing. To begin, I will explain the basic physiological mechanism behind coral bleaching. Corals live in a symbiotic relationship with microscopic algae called zooxanthellae. These algae photosynthesize and supply much of the coral host energy. When water temperatures rise by about 1 to 2 degrees Celsius above normal seasonal maxima for a prolonged period, corals become stressed and often expel their zooxanthellae. The loss of these algae causes the coral to turn pale or white and reduces its energy intake. If stressful conditions persist, the coral can die. Bleaching events have become more frequent and severe in recent decades. For example, the global bleaching events of the early 21st century affected large portions of the Great Barrier Reef and reefs in the Caribbean. Recovery is possible, but it depends on the severity and frequency of the events, the life history traits of coral species present, and local environmental conditions such as water quality. Now I want to discuss different dimensions of resilience. Ecological resilience refers to the ability of a reef to absorb disturbance and reorganize while maintaining core functions. Genetic resilience involves the presence of heat-tolerant genotypes or symbiont strains. And social ecological resilience refers to human management and the capacity of local communities to respond to change. Let us consider a concrete case study. In Palau, local managers implemented strict controls on fishing and land-based pollution in a set of protected bays. Over a decade, they observed increases in fish biomass and improved coral cover compared to unprotected areas. That example illustrates how local management can buffer reefs against some stressors, even though it cannot stop ocean warming. At larger scales, global mitigation of greenhouse gas emissions is essential. Models suggest that limiting warming to below 2 degrees Celsius above pre-industrial levels would greatly reduce the probability of repeated mass bleaching events. However, achieving that global target is slow and uncertain. Therefore, in practice, we need a portfolio approach that combines emissions reductions with local interventions and active restoration. Active restoration includes techniques such as coral gardening and assisted evolution. Coral gardening involves growing corals in nurseries and transplanting them to degraded reefs. Assisted evolution is more speculative and involves selecting or engineering corals or their symbionts for greater heat tolerance. Both approaches have potential, but also limitations. They are costly, may not scale up easily, and could have unforeseen ecological consequences. Another important point is the role of water chemistry. Ocean acidification reduces carbonate ion availability needed for coral skeleton formation. Even if corals survive temporary warming, slower growth under acidified conditions makes recovery much harder. Thus, improvements in water chemistry through global carbon reductions are crucial for long-term resilience. I also want to highlight the idea of refugia. Some locations exhibit natural resistance to warming due to local upwelling, shading, or mixing that keeps temperatures lower or more stable. Identifying and protecting these refugia can be a cost-effective conservation strategy because these areas may act as sources of larvae to repopulate damaged reefs. Finally, I will link science to policy. Effective reef conservation requires interdisciplinary work. Scientists need to provide managers with monitoring data and predictive models. Managers need to translate that information into zoning, pollution control, and sustainable fisheries policy. Communities must be engaged to ensure compliance and to benefit from conservation. In summary, coral reefs face multiple interacting stressors. Increasing temperature and acidification are the primary global threats. Local management, restoration, and protection of refugia can increase resilience. Local conservation measures can increase reef resilience by reducing pollution and overfishing. Combining local actions with ambitious global emissions reductions gives the best chance for reefs to persist into the future.
Listen again to part of the lecture. Then answer the question.
Local conservation measures can increase reef resilience by reducing pollution and overfishing.
For more TOEFL mock tests, as well as IELTS and Cambridge practice, visit www.spinta.org. We provide updated tests every single day, AI feedback for your speaking and writing responses, and access to a wide range of high-quality mock tests to help you prepare with confidence.